Hi, we're continuing our Chapter 7 notes with 7.2 hypothesis testing for the mean with sigma known. As we continue with the chapter, know that you already have the tools to answer the following questions. We have our knowledge from Chapter 6, confidence intervals, and it kind of ties together in this chapter. A hypothesis test is the probability of obtaining a sample statistic with the values as extreme of or more extreme than the one determined from your sample data. The decision rule for a hypothesis tests based on the p-value is shown below. All right, so this rule right here, it's gold. Make sure you have it in a post-it note handy or just highlight it in your notes. Decision rule based on a p-value. To use a p-value to make a decision in a hypothesis test, compare the p-value with alpha. So in these questions, we're going to be given some alpha to compare it to. If P is less than or equal to A, you reject your null hypothesis. That's your answer, that's your conclusion. Second, if P is greater than alpha, then you fail to reject your null hypothesis. And these are your two conclusions. Now, everything comes from what we said right here, this inequality. This inequality will help us move through these questions. So as you're working through the examples, and if you're ever unsure how we came to that conclusion, take a look at these two bullet points. Let's do example 1. The p-value for hypothesis test P is equal to 0.0237. What is your decision when the level of significance is A, alpha is equal to 0.5, and B, alpha is equal to 0.1. Okay, so when you're working through these problems, we're getting set up to work with comparing these alphas to our conclusion. Always have the setup P and alpha. So let's do A. Let's set up P and alpha. For A, my P is 0.05. I'm sorry, that's your alpha. We have this P of 0.0237. So my P is 0.0237, and I have an alpha of 0.05. Okay, which one's bigger? If you're ever confused, you can kind of block out those last 2 points and think of it as cents. What's more, 2 cents or 5 cents? And we see 5 cents is more than 2 cents, right? And that's our answer. Now, because we have greater than, which is our second option, we say we fail to reject. I'm sorry, it's less than. Right? I have less than, the first one is a less than or equal to. Because it's less than, we say we reject. So our answer is reject. That null hypothesis. B. Okay, so again, I want to write my P and then my alpha. Okay, my P for this problem we said was 0.0237. My alpha for B is 0.01. So what's more, 2 cents or 1 cent? 2 cents is more. Okay, because it's a second one greater than, I would say fail to reject. Fail to reject your null hypothesis. And this is how we work through our inequalities to reject or to fail to reject. Okay, we're going to be working with p-values. Finding the p-value for a hypothesis test. After determining the hypothesis test standard test statistic and the standardized test statistics corresponding area, do one of the following to find the p-value. A, for a left tail test, p is equal to the left tail. For a right tail test, p is equal to the right tail. Now C, be careful with C. For a two-tailed test, P is equal to 2 times the area of the standardized test statistic. So when you get an answer, if it's two-tailed, you have to make sure you multiply it by 2. Otherwise, we might get a false answer. Example 2. Find the p-value for a two-tailed hypothesis test with a standardized test statistic of z is equal to negative 2.23 and decide whether to reject the null when the level of significance is 0.01. Okay, so this is just a little refresher. So if I have my bell-shaped curve, I'm working with a p of negative 2.23. I'm sorry, a z-value. Now I want to relate it in terms of a p, a proportion, a percent in decimal form. So we need to change your z-score and change it to AP. To do so, you have to use your calculator. So we use second bars. So press second and then bars, and then you're going to choose normal CDF. But because we're working with z-scores, we're going to work with a mean of 0 and a standard deviation of 1. So to find this z-score and change it to a p-value, I have to enter it as, so working with this area, so my lower bound is negative infinity, and my upper bound is negative 2.23. So I write negative, a really big number, negative 2.23. My mean, we set a mean of 0, and a standard deviation of 1. And that will give us our p-value. You get something that looks like 0.01287 for a p-value. Now we have to write it as a p-value compared to our alpha. So I have a p-value of 0.012, and I have an alpha of 0.01. And we see that our p is slightly bigger, right? It's greater than. Now, if you've forgotten, look to the beginning. A greater than is the second case too, which says fail to reject. So let's go ahead and do that. So the answer is fail to reject. Your null, your HO. Okay, let's continue. Now let's focus on questions when we are left to find the p-value given some information, including the standard deviation. Z-test for a mean mu. The z-test for a mean mu is a statistical test for a population mean. The test statistic is the sample mean x bar. The standardized test statistic is the formula z is equal to x bar minus mu divided by sigma over the square root of n. When these conditions are met, 1. The sample is random. 2. At least one of the following is true. The population is normally distributed, or n is larger than 30. Recall that your standard deviation divided by your square root of n is the standard error mean, sigma x bar. All right, let's go ahead and put everything together. Let's go ahead and do example 3. So let's read the question. In auto racing, a pit stop is where a racing vehicle stops for new tires, fuel repairs, and other mechanical adjustments. The efficiency of a pit crew that makes these adjustments can affect the outcome of a race. A pit crew claims that its mean pit stop time for 4 new tires and fuel is less than 13 seconds. A random sample of 32 pit stop times has a sample mean of 12.9 seconds. Assume the population standard deviation is 0.19 seconds. Is there enough evidence to support the claim that alpha is greater or alpha is equal to 0.01? Okay, let's go ahead and list our claim. We're saying the mean pit stop time is less than 13 seconds, so less than 13. Remember, your HO has the equality and your HA is the opposite of your HO, right? Opposite of the null. Our claim gives us our alternative. So we have a mean average time of less than 13 seconds. So therefore our null would be mean, it's not less than, but greater than and equal to 13. Okay, we did half of the work so far. Okay, now we're gonna set up our problem. We're gonna use that formula that was given. Z is equal to x bar minus mu over standard deviation divided by the square root of n. So we're gonna need some pieces of information. We're gonna need x bar, we're gonna need mu, sigma, and we're gonna need n. That's gonna tell us our z-score. And we'll translate that into a p-value and then compare it to alpha. So let's make a list. I want to find my z-score, change to a p-value, and for that you use binomial CDF. Normal CDF, I'm sorry. Use normal CDF. And lastly, you compare your P and your alpha. Okay, so let's go ahead and find these pieces. Take the time to read the question a couple of times until you find these values. So our standard deviation, that is 0.19, right? Standard deviation of 0.19. We have a random sample of 32 stops. Okay, and we're comparing two means. One would be from our sample and the other one is from our whatever we're working with, right? So in this one, our x bar is 12.9 and our mean is 13. Okay, let's go ahead and work with that formula. So we have z minus mu over standard deviation divided by square root of n. That gives us z is equal to x bar is 12.9 minus mu 13 divided by standard deviation of 0.19 divided by square root of 32. Okay, we're going to use our calculator for this. Be careful, make sure you use parentheses. Remember, this is just division, and make sure you use parentheses when you're working through these parts. And you get a z of negative 2.98. Okay, we need to change this to a p-value. We found z, we need to find that p. So we do binom, I keep saying binomial. It's normal, right? We wrote above normal. We do normal, CDF. And that's going to give us our percent for our z-score. So we have negative infinity, so negative a really big number, negative 2.98. We have a mean of 0 and standard deviation of 1, so that we get a p value of 0.00144. All right, now I need to take the time to compare my p and my alpha. So my p is 0.00, let's say 1, and my alpha is 0.01. All right, so we see that we get a less than. When we have a less than, according to our two options above, we reject our null hypothesis. Now I have some good news. If all of this seemed like a lot of work, which it is, we can use our calculator to do all of our works for the p-value. It'll tell us the p-value. I think it also tells our z-score. To do so, we're going to go into our calculator and press Stat, scroll over to Tests, and you want to choose that first one, Z-Test. Okay, once you choose that, you're going to input this data. Make sure Stats is highlighted. All right, so you want to make sure you fill out your mean, your standard deviation, your X bar, and your N. Okay, then you have two options to have not equal to, less than, or greater than. And for this, you look at your HA. Your HA will help you answer this. So for our HA, we have less than. So we choose the less than out of our options. From there, so I guess you would say choose your tail. And from there, we can choose calculate. Once you press calculate, it gives you your z-score. So it results in your z-score, your p-value, and it also gives you your x-bar and your n. So it's really helpful. It saves you all the trouble. Now you do have to take the time to think about what your alternative is, because that lets you know what kind of tail you have, particularly if you have a two-tail. For a two-tail, remember, we have to multiply. We have right here, we have to multiply for C, we have to multiply our P by 2. And if you choose not equal to, it does that for you. It takes your P and multiplies it by 2. Okay, I'm going to go ahead and jump to this part of definition of rejection or a region. So a rejection region or a critical region of a sampling distribution is a range of values for which the null hypothesis is not probable. If a standardized test statistic fall in this region, then the null hypothesis is rejected. A critical value z0 separated the rejection region from the non-rejection region. So we kind of saw the shaded area in section 6.1, but we didn't talk too much about it. So we talked about only as the left tail, right tail, and two tail. While these tails house a lot, it's kind of like a danger zone or lava to make it more relevant. So if it falls on lava or a danger zone, then you reject it. If it's in a safe zone, then we fail to reject. And there you see those three images. Now, if you take a closer look, you can compare this in terms of z-scores. Or you can even use p-values. If you use p-values, you want to think of what percent attaches to that border. Let's take a look at example 5. So just as a question before, we want to go ahead and think about what we're given and um, find our claim and our two hypotheses, and then work through our problem. All right, so example 5. Employees at a construction and mining company claim that the mean salary of a company's mechanical engineers is less than that of its competitors, which is 88,200. A random sample of 20 of the company's mechanical engineers has a mean salary of 85,900. Assume that the population standard deviation is 9,500 and the population is normally distributed at alpha equals 0.05. Test the employee's claim. Okay, so We're going to do it by hand, but again, you can also use your calculator. I highly suggest you use your calculator, but take the moment to find where your claim is and label your alternative, your null hypothesis and your alternative. Those pieces are important. And of course, take the moment to label what your X bar is, your mean, your standard deviation, and your N, because you're going to need those for your calculator. All right, so our claim is less than 80,200. Okay, because it's not equal to, this will apply to alternative. So I have a mean is less than 88,200. We have then a null hypothesis of mu or mean greater than or equal to 88,200. So you'd like to take a moment to pause the video and think about what each one of these values are. We have a mean of 88,200. We have a sample mean X bar of 85,900. We have a standard deviation of 9,500. And we have an N, a sample of 20. Okay, let's do some work. So we have to find that Z. We find that Z is equal to X bar minus mu over your standard deviation divided by square root of N. Okay, we fill that out. We have 85,900 minus 88,200 divided by 9,500 divided by the square root of 20. Use a calculator. You get Z is equal to negative 1.0827. You want to change it to a p-value using normal CDF. So you have normal CDF. You use a really big number, negative 1.027 and 0, 1. You'll get that P is 0.1395. And then we compare P and alpha. My P is 0.1395 and my alpha is 0.05. Which one's bigger? We get a greater than. A greater than means fail to reject. And that is our answer. We failed to reject our null hypothesis. Now, if I want to relate this to a curve, so we have our bell-shaped curve, and we're working with a p-value of 13, and we have an alpha of 0.05. So this alpha, if I change it to a percent, it's 5%. So therefore, the complement of that is 95. We're working with a tail of less than, so we want to find that 5% or 0.05, and that 95% or that 0.95, that's a safe zone. So where does our p-value fall? Our p-value gives us a percent. So we have a p of 13, which is bigger than 0.05, 0.1395. And it's not precise, I'm just showing it's bigger. So therefore, it's in the safe zone. So we would fail to reject. We don't have to reject it. We would reject it if it fell in this danger zone. That would be trouble. Then we would reject. This is our reject area. And anything bigger than that, we would fail to reject. So that's using this idea of tails and figures that we have in our chart. And again, we can just use our P and our alpha and compare them. And also on top of that, we can use our calculator. And honestly, I highly encourage you to use your calculator. Not just only to calculate Z, but it can do all this calculation, give you Z and P. Remember, it's test, highlight to, oh, press stat, highlight test, and it's that first one, Z test. You just have to take a moment to find these pieces of information. You for sure have to find your claim so you can label your HA, and then find the mean of your population, the mean of your sample, your standard deviation, and your N. Now, the reason it's important to label your alternative, your HA, is because you have to say what kind of tail you have. Left tail, right tail, and you can tell which tail by your inequality. It's pointing to the left, so you have a left tail. If it's pointing to the right, greater than, then you have a right tail. If it's a not equal to, then you have the not equal to option. Okay, and this is pretty much the full concept of the section. If you have any other questions, feel free to email me or to post your question on our discussion board. Thanks.